Hello, and welcome to Badger Talks Live, which brings exciting happenings, resources, and talent from your UW flagship campus to the people of Wisconsin and beyond. I'm Katie Brown, originally from Milwaukee, Wisconsin. I am a second-year graduate student in the geography department, where I'm mapping thawing permafrost in Arctic Alaska for my master's thesis. I am pleased to introduce my advisor, Professor Andresen, Assistant Professor of Geography. Join Professor Andresen on an exploration of how the Arctic region is evolving, with a focus on the effects of climate change on permafrost and the potential consequences of increased methane emissions into the atmosphere. Dr. Andresen is an assistant professor in the geography department at UW-Madison, and his research explores the effects of climate change in Arctic wetlands and how these changes influence land-atmosphere carbon exchange. Please welcome Professor Andresen.
Thank you, Katie, for the introduction, and thank you for the organizers. I'm pretty thrilled to be here today and share a little bit of the work that I do up in the top of the world. And all of these research has been funded by the National Science Foundation and also the Office of the Vice Chancellor for Research and Graduate Education. My question to you is, what is the first thing that comes to mind when you imagine the Arctic? It's likely that you're thinking about ice and a very cold region. And both of those answers are correct. Well, there's sea ice on the Arctic Ocean and an ice sheet on Greenland. The surrounding land is frozen underneath the surface. It actually represents a significant portion of the northern hemisphere, from parts of the continuous US, large sections of Canada, Alaska, Russia, and even China have ground frozen. This is what we call permafrost. And it looks something like this. Permafrost is frozen ground, and sometimes it reaches almost a mile in thickness in some areas. It is composed by a combination of mineral soils, many different forms of ice, and a lot of dead plants and animals like bisons and woolly mammoths that roam this region over thousands on the last thousands of years. Think of permafrost as the freezer of the earth. And what happens when our freezer stops working? It actually, the food starts spoiling and decomposing. And it's actually what's happening at the top of the world. As permafrost thaws, it is actually exposing all these dead plants and animals to microbes, which decompose the carbon and emit greenhouse gases, such as carbon dioxide and methane, into the atmosphere. To make things worse, the Arctic has been the most affected in terms of climate change, which is impacting certain regions of the Earth differently. The Arctic has actually warmed 4 times the rate of the global average. We're definitely seeing hot times in cold places. For example, in northern Alaska, we have seen an increase of 5 degrees Fahrenheit over the past 50 years. This phenomenon is what we call polar amplification. And it's due to several factors, where the main factor driving this polar amplification is the loss of sea ice in the Arctic. And this sea ice in the ocean acts like a mirror to solar radiation. And when that sea ice is gone, open water absorbs more radiation, changing the regional temperatures and climate of the area. Scientists actually project that half of the permafrost will be gone in the next 50 years. And these changes will significantly change how the Arctic landscape looks and how actually it functions. And it's likely that these changes will increase greenhouse gas emissions from permafrost to the atmosphere, which actually is going to lead to more warming, acting as reinforcing warming feedback to climate. To really understand how this reinforcing feedback cycle will influence global temperatures, we scientists use computer models to represent Earth processes. However, these models ingest field observations and measurements, such as how carbon is being cycled between the permafrost region and the atmosphere. And these field observations, that's where I come in. I am a multidisciplinary earth scientist, and my focus is to measure and quantify how these regions changing, and how the changes influence carbon emissions. Particularly, my research focuses in the Arctic, in Arctic wetlands, which are underlined by permafrost. This permeable layer acts as a layer for wetlands to thrive in this environment. This image is an Arctic coastal plain in northern Alaska. This is actually the ancestral lands of the Inupiat people. As you can see, most of this land is dominated by wetlands and lakes and ponds. And one of the things characteristics about these aquatic systems is that they're one of the main producers of methane to the atmosphere. And methane is 30 times more potent greenhouse gas than CO2. So it's really critical that we measure and quantify methane contributions from Arctic wetlands into the atmosphere. What has scientists alarmed is that the global methane concentrations in the atmosphere are rising at actually an alarming rate over recent decades. Which brings us to the question, is permafrost thaw in Arctic wetlands a culprit of this increase? And the answer is that we don't know. Even though wetlands contribute to about half of methane contribution to the atmosphere, this dramatic increase is actually uncertain. I have been going to the Arctic over the past 15 years, and I actually witnessed some of these changes myself. But before me, scientists have actually studied the system, producing invaluable data sets that help us understand the long-term changes in these ecosystems and the potential contributions of methane to the atmosphere. And using these historical data sets and observations, we have been able to understand how these systems have changed over the past 50 years. Some of the things that we found is that Arctic ponds are actually shrinking and disappearing in the landscape. About a third of the area of ponds have been lost over the past 50 years. When we look at the ground level, we see that a lot of these decreases, not because these ponds are drying, but because these plants are actually moving into these systems, encroaching the open water areas. And why is this concerning? Well, actually, it turns out that aquatic grasses act as methane straws, conducting gas from the soil into the atmosphere. Here's a picture showing the whole structure that these plants have called parenchyma. And this structure helps plants to become buoyant in the water and stay vertical. However, they use methane from the soil for that, and these mixtures actually cycle through their stomata and their leaves and release into the atmosphere. And we have found that methane plant transport is the #1 source of methane in these wetland ponds. To better explain what is happening, what I've seen the changes over the past 50 years, this diagram highlights these systems. What I've seen is an increasing temperature that has enhanced permafrost thaw. And increasing temperature and permafrost thaw is actually a big contributor of nutrient inputs into these aquatic systems. Think of nutrients as the fertilizer for your garden. So with warmer temperatures, and more fertilizer, these plants actually are encroaching these aquatic systems and increasing biomass. All these biomass production is actually being decomposed, and also carbon from the permafrost is also being liable for microbes for decomposition and emitted to the atmosphere. And we see an increase about 70% in methane emissions from increases of biomass in these aquatic systems. What this is doing is actually reinforcing that cycle of climatic feedbacks to the climate. To this date, however, the net carbon balance of these aquatic habitats is not really being well understood. We really have been not being able to quantify very accurate how much methane is actually being emitted from these systems at the landscape scale. And it is uncertain how the role of Arctic wetland ponds on the timing and strength of the permafrost climate feedback. With the support of the National Science Foundation, we're deploying 80 covariance sensors that will allow us to continuously monitor CO2 emissions in this landscape and methane emissions in this landscape. Think of these sensors as sensors that actually measure how much methane is being emitted into the atmosphere and how much carbon is also being uptaken by these systems, and understanding the net balance of land atmosphere carbon exchange. We're also using state-of-the-art drone technology equipped with multispectral sensors and laser scanners that, combined with machine learning mapping approaches and techniques, will allow us to quantify changes in these ecosystems and match these changes with how much methane is emitted from 80 covariance measurements. Ultimately, this project aims to answer what are the contributions of these systems to the global methane budgets. Even though Arctic methane emissions are significant, they actually represent a small portion of the global methane emissions. As a matter of fact, human activities contribute to most of these emissions to the atmosphere. And wetlands or natural resources due to minor production of methane to the atmosphere. So the IPCC report, International Panel on Climate Change, represents a panel of earth scientists across the globe, and they have recently released a report that shows the temperature will continue to increase over the next 100 years. And one thing that I want to highlight is that depending on greenhouse gas mitigation strategies, in other words, how much greenhouse gases we emit to the atmosphere, we can curb some of these effects of climate change and some of the effects of Arctic wetlands methane emissions as well. And for example, an increase of 1 Celsius versus 3 Celsius, comparing between a high emission scenario and a low emission scenario, can make actually a big difference. We're talking about a difference that can make a hurricane be a category 1 versus a category 5. And scientists have been actually taking a lead in addressing climate change, not only try to forecast what is happening in the future, but also scientists play a key role in understanding and developing new technologies for minimizing climate change impacts. Technology is actually playing a crucial role in addressing climate change, and because technology facilitates the use of renewable energy and the use of energy sources. And these technologies are becoming increasingly efficient and cost effective, making clean energy more accessible and reducing reliance on fossil fuels. Also, developments such as data analytics and artificial intelligence are actually helping us to really improve the management of environmental resources. Also, the use of satellite sensors and drones and predictive modeling, it's actually improving scientists to track climate change, to pinpoint climate patterns and identify areas of risk and optimize resource allocation for more sustainable practices. Another big area where scientists are actually helping climate change is the innovation of transportation, such as electric vehicles and intelligent traffic management systems, reducing carbon emissions and improving air quality. Other things such as smart grids and energy efficient infrastructure are being deployed and optimized energy consumption, reducing the waste and greenhouse gas emissions. I often get the question from people when I tell them I'm a climate scientist, earth scientist, what can I do to prevent climate change or to slow down climate change? And there's a lot of different things that we can do to slow climate change. And we as individuals can do a lot, We have the power to make a difference. We have the power to slow climate change. And we have the power to provide a better future to our children. As consumers, we make sustainable choices, such as reducing our energy consumption, opting for different energy sources, and supporting environmental friendly products and services. And these are just a few examples of it. However, we can also make a bigger difference when we act together. Voting enables us to elect leaders who prioritize environmental issues, support renewable energy policies, and advocate for sustainable practices, ultimately driving systematic change and the implementation of impactful climate policies that will help prevent hot times in cold places. Thank you. And thanks for tuning in, and feel free to post any questions in the chat and I'll be happy to answer them after the live stream.
Thank you for watching this Badger Talks live event produced by the University of Wisconsin-Madison through UW Connect's outreach and the Office of State Relations. Follow us on Facebook and YouTube to see the library of past recorded talks. Please visit badgertalks.wisc.edu to see the schedule of upcoming talks, sign up for the Badger Talks email list, and search the roster of over 400 UW experts who are available to give talks on important issues in your Wisconsin community.